So the steady state approximation is an important approximation that's used in chemical kinetics to simplify the rate laws that we can get from reaction mechanisms. And so let's look at these plots. These are looking at this is the same reaction mechanism that we were considering in the previous video. So we have A going to I, and then I, stop moving around, and then I going to P with K1 and K2. And these are some plots from your textbook looking at some specific examples. These kind of correspond to the examples we talked about in the previous video, where we have, in one case, K1 is 10 times K2, meaning this is the case where K1 is bigger than K2. Right, and so this is the example where the first step is the rate limiting step. And so here we can see the exponential decay of the initial concentration of A, right? So this is following that same, and we can see it's the same for both of these, that one. But we can see our product grows in at that sort of that same rate. Whereas instead for our second, right, where the value of K2 is 10 times K1, right, where our second step is the fast step, then we see a different behavior here, that the product grows in much faster. So that's sort of a visual representation, right? You can see that this gets bigger on the right-hand side. The concentration of P increases at a faster rate than it does on the left-hand side. The other important thing here, though, is to look at the intermediate, what happens to its concentration in these two scenarios. So the concentration of the intermediate on the left-hand side rapidly increases, and then as because K1 is the fast step, we get a lot of intermediate very quickly, and then as sort of the second step catches up, then the intermediate starts to decrease. On the other hand, in the second example, where the second step is the fast step, the intermediate gets produced, and then as quickly as it's produced, it gets used up. And so it very quickly approaches a very low concentration, but stays about the same. And what we can say here is that the rate of change of this concentration over time is approximately 0. And this is the steady state approximation, right? That you can take an intermediate, if it's being used up as quickly as it's being produced, then we can say that the concentration of that intermediate, the change in that concentration, not the concentration isn't 0. It's still present at a very small amount, but the change in the concentration is approximately 0. Now, you can't always make this approximation. It needs to be a situation like we have on the right-hand side, where the intermediate is being used up as quickly as it's produced. If we instead have the case on the left, we can see that dIdt is not 0, except for at the very top of this curve, and it doesn't stay there, right? That's the only point where it's 0. Whereas here, it's basically flat along this curve or across the entire thing. So how would this work out in terms of our mathematics? So again, coming back to our rate laws that we could write for this particular mechanism, right? We have dA dt. That one's still straightforward. We're losing that according to this rate law. We can write all the same rate equations we had before. So we're gaining I from the first step. We're losing I in the second step. And dP dt is equal to K2I. Right, so these are the same equations we had before. And the assumption we make here in the steady state approximation is that this is approximately equal to 0. Okay, and what that does is it lets us solve for the concentration of I in terms of A. And that's generally what's useful about the steady state approximation, is it lets us find the concentration of the intermediate in terms of things that are not that intermediate. So we can say, okay, the concentration of I, assuming the steady state, so we'll write this ISS, we just solve this for I, right? So we get a minus K1 times A divided by minus K2. So we can say, okay, well, those become positive. So this is our steady state approximation. That's the concentration of I. It's a consistent value, right? We can also use what we know about the solving this, we know what the concentration of A is equal to. Right? This is the equation that we saw before. And so we can plug this expression in for A here, and we will get that the steady state concentration of our intermediate is equal to K1 over K2 times A naught e to the minus K1t. So that's just, again, plugging this expression here into our expression that we got for the steady state. Okay, and so again, this is specifically valid if the steady state approximation is true. Okay, so let's think about when is this going to work? What are the conditions? We've sort of already said it, but just mathematically showing this again. All right, so how does this change with time? Okay, so let's take. We want to show that this is actually going to be 0. So let's take the derivative of this with respect to I, because we want to show that this should be 0. Okay, so we'll get, we're taking the derivative of an exponential, so we'll get a minus K1. So di dt under steady state will give us minus K1 squared over K2 times A naught e to the minus K1t. And this will go to 0 if this first term goes to 0, right? The exponential term won't go to 0 until time gets really large. Okay, and so when is this term going to go to 0? Well, it'll go to 0 if K2 is much, much bigger than K1 squared times A naught. That fraction will be really small if K2 is big, right? Because it's the only thing in the denominator. And so this is essentially it's a little bit circular, but this is the case that we considered on the right-hand side, where K2 is much bigger than K1, and we can also include the fact that this has to be multiplied by this concentration as well. So yeah, so this shows the conditions under which you would expect the steady state approximation to work, and then we can solve our specific equations to get the same thing we got in the previous video when K2 was much, much bigger than K1. In the next video, we'll look at an example of applying the steady state approximation and how we can use that to solve for a rate log given a mechanism.